Hey, AP physicists. I promised you yesterday that I would record a quick video for you to help talk about the analysis of data that we started doing yesterday. So I don't want to belabor the point, but I just want to make sure that you're okay with what we did yesterday and then move on so that we can see the point of all of this. So just a reminder from yesterday, we spent some time with Google Sheets trying to analyze the data of the ball going down the ramp. And the ultimate goal that I was trying to explain to you yesterday, but I just want to make sure, is that we're trying to go now from our little buggies that were moving at a constant speed across the floor, which was an interesting thing. And we were measuring the motion of those and found these nice straight lines, right, that are pretty easy to understand when you've got a displacement versus time graph, to now something a little bit more interesting, and that is the ball going down the ramp. That motion, instead of being a nice constant motion, it gets faster and faster. Oh, my stylus is not acting nicely today. And what we found yesterday when we were working on this is when we graphed just the motion of the ball going down the ramp, that instead of getting a nice straight line you do it with it as you do with the buggies, we got this curve. Okay, so that was kind of the first thing that we wanted to figure out. And then I was trying to encourage you to think about ways that we could take this this graph that's curvy and harder to analyze. I mean, one can do it, but it's just a little bit more challenging, and put that into a straight line, something that we know and can look at very, very easily. Okay, so the whole goal of this is to go from what we call constant velocity motion into the realm of accelerating motion. And to do so in a very organic and kind of build from the ground up sort of way, as opposed to me just telling you the variables and telling you the equations. I want for you to see it so you can kind of get an appreciation for where it comes from. So yesterday we got onto Google Sheets and we had some success of developing graphs for our original data. So these are just screenshots from my Google Sheets, right? So I've got time and then the distance. So these three columns are different ramp heights. And we can see from this nice data that you get these curves. Again, exactly what you predicted would happen when you have the ball going down the ramp. But then we said, well, curves are fine. And for a lot of you, curves you can handle, but lines are everybody's best friend when it comes to graphing and interpreting graphs mathematically. And so we talked about how going from a curve that we could say that, let's just kind of walk ourselves back through this, that a line is y equals mx plus b. Again, I'm not going to worry about the plus b for now because that's just moving it up or down, right, to get a different y-intercept. And trying to get something that is a parabola, which is y equals kx squared, trying to get something that's parabolic into a straight line. So the suggestion that I made that I'm hoping seems reasonable to you is that if I make x squared the variable as opposed to just x, then that will what we call linearize or make into a straight line the function that we had. And so instead of having this curve, what we get, so this is y and x, this was y and x as well, just for clarity's sake. To linearize that parabola, then we've got y and we've got x squared on our x-axis, and then that generates a straight line. Okay, looking at that in terms of the ball, basically what we're doing is we're going to leave the position on the x-axis, or excuse me, on the y-axis, that's over here. And then instead of doing time down on the x-axis, we are going to square the time. So I'm going to leave position on the y-axis, and I do time squared. And my suggestion was that would give you a straight line. So we tried to do that. We had some success, but I just wanted to show you again a screenshot of my Google Sheets to show you that with position, I labeled it distance here, it really should be position on the y-axis and time squared on the x-axis. Yes, indeed, you do get something that looks like a line. Now, as I show you further and further into this, some of you are going to argue, well, that doesn't really look like a line, but I want to bring you back to where we got this data from, right? This is literally from that ball rolling down the ramp, and the precision with which you got that data could have been better, let's say. So I want you to kind of just look at those data points as, well, yes, indeed, they are more of a line than what we had before, okay? The better our data, the better the analysis would be. So just roll with me, okay? All right, so now what I want to do today is to use that idea to then develop an idea of acceleration. Acceleration, again, being a change in velocity as the object is moving. Okay, so we're going to do this together. This would be a great thing for you guys to write down and kind of follow along with me so that we can get through this. So for some of you, we wrote this down a little bit yesterday as well, just kind of giving you a heads up as to where we're at. So I'm going to go ahead and graph here. This is position versus time squared. That did indeed give us a line, the ones that we just saw. We also we wrote down, well, that's going to be like position is equal to some sort of slope times time squared. We looked at the units of the slope. And we said, well, that's meters per second squared. And some of you said, oh, well, that's interesting. Meters per second squared, that has something to do with acceleration. It does. It does. It may or may not be exactly acceleration, but let's just hold on to that idea. The units of the slope are meters per second squared. So then here's the fun part, is that this is one way to linearize our data, just to take that time and square it, which Google Sheets can very easily do for us. But then there are a couple other ways to do that as well. And one of the ways that I mentioned yesterday was by graphing velocity on the on the y-axis, excuse me, and time on the x-axis. And we didn't really go through how to do this, but let me explain just very briefly how one might do this. Okay, for my friends in calculus, this is going to make a little more sense. My non-calculus friends, bear with me, but I think that you can get the idea. When we're finding the velocity from a position versus time graph, you want to find the slope, right? And so for this graph, because it's curved, that means that the slope is changing. So the slope might be like this down here, and then it may be like this over here, and then it might be like this over here. And so you can see that that sloped line, or the slope of the curve, varies. That's the whole idea. Like, that really is the first semester of calculus right there in a nutshell. Mueller would agree. Just want to put that out there. He doesn't disagree with that. So the idea is to find the slope here, or the slope here, by finding these 2 points and doing a rise over run. And that's going to be different than the rise over run here, different from the rise over run here. Okay. And so when I did this in Google Sheets, basically I took these two distances and found the change in those divided by these 2 times, found the change in those to find the slope at this point, okay? And then the same here and same here. And when I did that, then this is the graph that I got. So it's just the average velocity at any given point, but it's the velocity, and then I left time on the x-axis. And again, the data is being manipulated a little bit, so the linearization is not perfect, but you can see that those data points do line up for each of the cases. So we're going to go ahead and write that down. So velocity versus time graph, we do also, sorry, I'm trying to keep my colors consistent here. We do also get a nice straight line. The equation for this line would look something like v is equal to some sort of slope times t. And if we look at the units for that slope again, you've got meters per second is the change in y, and seconds is the change in x. So we're dividing fractions, which is like multiplying by the reciprocal. So that's going to be like meters per second times 1 over seconds, which, oh my gosh, gives us meters per second squared. Okay, again, looks something like an acceleration. I feel a little bit like a late night infomercial host because I'm going to say, but wait, there's more. There's another way that we can make a linearized graph from the data that you collected from the ball rolling down the ramp. The third way to do it is to do velocity squared on the y-axis and position on the x-axis. Now you may be saying, Ms. Carbling, we've already linearized the graph twice. Why do we need to do this? And this is going to be a moment where I'm going to say, just trust me, be patient, and you'll see why in just a moment. But I am going to claim that that's going to be a straight line and that we're going to double check it. And we're going to, oops, it was not there. Hold on just a second. Let me just pull it up this way. I thought that I put it in there, but it really, I promise, is there. There it is. So right over here, you can see velocity squared on the y-axis and distance on the x-axis. Okay, so again, the data gets a little bit goofy because again, I'm finding that velocity, now I'm squaring it, so I'm kind of calculating on those points a little bit more, which makes it a little funny, but those are pretty much linear. So we're going to call that good and put that into our notes here. Take a look here. So this is going to be v squared times some sort of slope and then times distance. Again, just to make sure that we're being consistent, we're going to look at the units of the slope, and we've got, this is going to be meters per second squared on the y-axis because we've got velocity squared here, divided by distance. Again, with the fractions of fractions and things like that, we've got meters squared per second squared times 1 over meters. So I've got a meters on the top and a meters on the bottom that'll cancel, and this will give me units of meters per second squared. So in all three of these situations, I've got a slope that has the units of meters per second squared. We know that meters per second squared is a unit of velocity. How do we know that? Why are you telling me that, or just trying to force that down my throat, Miss Kay? Well, let me show you just real quick. So acceleration is a change in velocity over time. So change in velocity, well, that's really what this one is doing right here, right? Change in velocity over time, meters per second, that is the unit of acceleration. So now, to figure out which one of these is acceleration and how that all fits together, now we're going to take information from the graphs that we got from Google Sheets. And I'm not going to bounce back and forth. I'm just going to write down information for time's sake. So the next step of what I would do is to look at the slopes. We're just going to take a little quick gander here, okay? So this was height 1. Oh, come on, stinker. So here's maybe. One, height 2, and height 3. And then I found the slopes for each of those in each of these 3 graphed cases. So I just want you to look at this data real quick, okay? So I got 2.99, 7.35, and 13.1. And if you don't want to copy this down, that is absolutely fine. This is more of a just kind of take a look at it, see if you see any patterns. 16.8. And then finally, I got 7.49, 22.3, and 33. And these are, I believe, in centimeters, whatever. It doesn't, in this case, really matter. I just want you to look at the values of the numbers. And what we see are that, first of all, the slopes are not the same, which means that even though they've all got the same units for the slope, their values are different, okay? They do have some relation, okay? Again, the data is not perfect. One of the things that student scientists often get fussy about is that things aren't perfect. That's true. There is a lot of error, again, in this data, but you may be able to notice as you look at this data that these ones are all smaller than these, and that the ones over here are all larger. And to some extent, we can kind of say that the ones that I've just highlighted in blue are about half as big as the yellow ones, and the ones that I've highlighted in green are about twice as big as the yellow ones. The more data we take, the more precise our data, the better it's going to be, but you can kind of agree that we see that process. And from that, we can take these equations up here and fill in some more information, okay? So I'm going to take those equations from above, I'm going to write them down below, and this part again would be something that I would write down if I were you, kind of some important stuff. We'll see if my stylus is going to cooperate for the rest of this today. Come on, team. All right, so this one over here, this middle one, is really change in velocity. That's the definition of what's going on when we are looking at our y-axis, right? Change in velocity is equal to that slope, which is indeed acceleration times time. This, in fact, is the way that we usually would define acceleration, that acceleration is change in velocity over time. That is worthy of a big box. That is worthy of some stars. That is worthy of your attention and appreciation, okay? So what do we do with these other ones? The one that's the first one we did, the one, well, yeah, let's do that one first. The first one that we did was the position versus time squared. So if I claim that that middle one, the slope is actually acceleration, then this change in position equals something times time squared. Well, if these guys are acceleration, and the slopes that I'm getting in the first one, in the blue one, were half as acceleration, that really actually is what that slope represents. It represents half of the total value of the acceleration for the ball rolling down the ramp. Okay, so that's kind of exciting. Now, there's one other little piece here that we haven't put in, and that is that our ball rolling down the ramp started at a velocity of 0. It wasn't moving. You released it from rest, which is what I asked you to do for simplicity. Last time, or last unit, we did spend some time looking at things where we had something moving at a constant velocity, and we said that delta x was equal to its velocity times time. And I'm actually going to use these two equations. I'm going to put them together, okay? And I'm going to say that the change in position really is equal to any sort of initial time, or excuse me, initial velocity times time. So this is the if it's moving at the beginning, plus any acceleration that it experiences. Okay, so this is the constant velocity or initial velocity part, and this is the acceleration part. This is really, friends, the equation that we used both last unit and now this unit all put together. This equation right here, also worthy of a box. This equation right here will become one of your best friends as we work through the kinematics units, okay? I've said kinematics, that word, a few times. Kinematics just means analysis of motion. That's it. It's just a fancy word. It's one of those things, if your parents ask, what'd you do today? I derived the kinematics equations. That sounds really fancy. Give it a shot. They might be like, whoa, that's awesome. They should be, because it is. All right, last one. So this third one, if we remember, because it's been a couple moments since we looked, is change in velocity squared equals some slope times distance, or position, change in position. So we're going to write that down here. So this is really final velocity squared minus initial velocity squared, because we're looking at the difference in those, right, is equal to something that we don't really know times a change in position, okay? So the change in is really just acknowledging that it's not staying constant, that delta is not necessary to be there, but just kind of get your head around that change in idea. That's why I left it there. Now, on our first one, I told you we're going to call this just A, acceleration, plain old. partially to keep it simple and partially because that's how we've defined it. Okay. Then we said over here that we had 1/2 a because our slopes going this way were about half as big as that middle column. Moving the other direction, remember we said that they're about twice as big. So instead of just writing a, we're going to write 2a. All right. And this right here, I don't have to do any manipulation or algebra with that one. I'm going to go ahead and put a box around that as well. Okay. So that's a lot of kind of writing and thinking. But friends, what we just did here is something that few physics students actually get to do, and that is to see exactly where the primary kinematics equations come from. Tomorrow I'm going to give you a copy of the AP Physics equation sheet that you're going to use all year long. But I wanted to show you just a quick picture here of what's on there. So this big picture on the side here is just a screenshot of the equation sheet. Like I said, I'll give it to you tomorrow. It looks pretty scary, which is why I didn't want to hand it out while I'm not there. But I want you to just take a little look right over here at the first 3 equations that are on that equation sheet. This one, that top one, is actually the same, whoops, come on, the same as saying that A is equal to the change in, wow, my stylus has decided to act up a little bit. The change in velocity over time, because we could say VF minus VI over T. And solve that for A. This second one is, holy bananas, this is annoying, is the same as the first equation, that pink equation that we wrote down. This is the change in position part, initial velocity times time, and 1/2 AT squared. And the last one right here is indeed that last equation. We've got a change in velocity final squared minus velocity initial squared. They just moved one over. And then 2a delta x. So friends, just now we derived all 3 equations. That is super awesome. Okay, I am going to have you take a look at some workbook pages today and also a couple of fairly simple kinematics problems, and we will go over stuff tomorrow. It'll be great. Thank you so much for your attention. I hope that this helped and made sense, and I will see you tomorrow. Have a great day, you guys.